Welcome back. This time we're going to do a problem with a spring in it. Okay. The problem goes something like this. You are an employee of a company that makes these little toys here, among other things. Okay. The way this thing works is you push the head down until this suction cup attaches to the plastic base here. And then they will stay stuck together for a short time. After a short time, the suction cup will come loose. The head will jump up, and the whole thing will spring up into the air about 30 centimeters. Okay? And so the idea then is that your job is to purchase the springs for this thing, and you need to figure out what spring constant you need so that you can order a bunch of these. So, what we know about this thing is that the entire thing has a mass of about 5 grams. When you push the head down, the spring compresses by 1.5 centimeters, and the whole thing jumps up in the air about 30 centimeters. Okay? And so we want to figure out what spring constant we need in order to make that happen. So, the way we're going to do this is we're going to use conservation of mechanical energy. And anytime you use conservation of mechanical energy, it's always going to start out the same way. You're going to say that the energy at one moment is equal to the energy at some other moment. Okay? Now, then you got to ask yourself what types of energy are involved here. And in principle, we've got kinetic energy because the thing's going to be jumping up. We've got potential energy from the spring. And also, because there's vertical motion going on, we've got gravitational potential energy as well. Okay? And so we're going to have to include all of these things. So, let's see. That means 1 half mv1 squared plus 1 half k x1 squared plus mgy1 is equal to 1 half mv2 squared plus 1 half k x2 squared plus mgy2. Okay, where basically point 1 here is down at the bottom, just at the instant that the suction cup is being released, and point 2 is up at the top when it's about 30 centimeters above where it started. Okay? Now, we can actually get rid of some of this stuff because down here at the bottom, at the instant that the suction cup is released, it's not moving yet. Okay? And so I'm going to say V1 is equal to 0. Also, with gravitational potential energy, remember that you can basically set the height, y here, equal to 0 at any height you want. And so I'm going to say it's 0 at the bottom and it's 30 centimeters at the top. So we'll get rid of that. Okay. And then, of course, point 2 here is when it reaches the top of its motion. At that point, V2 is going to be 0. Okay, you learned that last semester. If you throw an object up in the air, when it reaches its highest point, if it's traveling straight vertically, its vertical velocity is going to be 0. Also, at the top of the motion, the spring is neither stretched nor compressed, and so I can say that x2 is also 0, and y2 is going to be, that's where our 30 centimeters comes in. So I've really got this down to just 1 half k x1 squared is equal to mg y2. Okay? In other words, what happens really is that our spring potential energy is converted into gravitational potential energy. So let's put in what we can then. 1 half k x1, that's the amount by which the spring is compressed, which is 1.5 centimeters. Let's do this all in SI units here. So this is 0.015 meters squared equals the mass, which is, again, in SI units, that's 0.005 kilograms times 9.8 meters per second squared times 30 centimeters, which is 0.3 meters. Okay? And so notice I can take all of this, I can solve it for k, And when I do that, I get K equals 131. And since I've been working in SI units all along, I know that I've got to get the SI units for spring constant. And spring constant, remember, is, it's basically force over distance, so it's going to be newtons per meter. And so that's my answer.